All right. Sketching the derivative can be kind of tough, but that's why you're here to learn. So before we begin anything too major, let's just understand what the derivative graph depicts. So let's say we just have a simple graph right here. This is y, x. We just have to remember when we're sketching our derivative, you don't want to just follow that graph. Like, in fact, I'll draw it in blue on this graph that I just drew. You don't want to end up just like tracing the graph because now you're just plotting the y point. But do remember that our derivative graph is actually a graph of x and y prime. Quick disclaimer, read what I have below, but I essentially throughout the video, I keep making this mistake of when I'm talking about the derivative of y, I keep using y1. However, that is not correct. It's supposed to be y prime or dy dx. And when I say y prime, you have like an apostrophe next to the y. Think of it kind of like an exponent, even though it's not, but it's kind of like an exponent of sorts. That's how it actually is supposed to look, meaning the slope at each individual point along this graph. Each one I'm circling and infinite more. So just remember that. All right, let's just go over some tips right before we get into some problems in order to sketch the derivative. So first, you want to find critical points, such as when our derivative value, or f prime of c, equals 0, or when our derivative is or does not exist. Because let's go with the first one, where our derivative value equals 0. In most cases, except when it's a point of inflection, on some cases, that'll be a min and max, or local extrema, which is basically like a peak or a valley on our graph, these points right here. And when we get those, we know our slope at those points is 0, meaning the tangent line, the slope of that tangent line is 0. And that'll allow us to, when we're sketching our derivative graph, to cross the x-axis at that point. And then to elaborate on the do not exist, this is such as when there's a cusp, a corner, an asymptote, or a hole, our derivative graph is going to act a little bit different. In fact, we aren't even going to have a kind of logical derivative at that point, not one that's smooth at least. And then I'll kind of show you how that works in a couple of examples. Next, we want to find some point of inflections because this is also another important point for us to recognize. Even though it might not be a min and a max where we cross the x-axis, it'll show us where our extrema are on our derivative graph. So we'll see how that works. Finally, just in case you're a little lost and you don't really know where to start, especially on complex polynomials, it's always important to approximate the slope at the beginning and at the end of a graph. It'll just kind of help you get started and connect all the dots. All right, so let's jump into our first example. So right here we have a graph that kind of looks like a x squared, or like its parent function is x squared, or maybe the function actually itself is x squared. Anyways, that's beside the point. So let's use our tips in order to kind of understand how we'd sketch the derivative, plus a couple more that I might not have mentioned. So first, let's find our critical points, meaning when our derivative is 0. So if we kind of look along this left graph, which is not our derivative, but our original graph, if we look at x equals 0, looks like we can draw a horizontal tangent line to that point. Meaning at x equals 0, we actually have a critical point, a local minimum. So we can draw that on our graph, kind of mark it down on our derivative graph, meaning we will cross the x-axis at that point. All right, next let's look whether when we're increasing and decreasing, which is actually not something I showed on the tips, but this is kind of the essential thing behind sketching the derivative. So let's look when we're increasing and when we're decreasing. So let's start left to right on our original function. So if we're looking along here, going left to right, it looks like we're decreasing. So I'll just draw a negative sign. But once we get past this critical point right here, this local minimum, we start increasing, positive. So we know when x is less than 0, in fact, I can write it out to make it easier. When x is less than 0, we are decreasing, meaning f prime x, or actually it'd be y, so I'll do y prime. Y prime is less than 0. But when x is greater than 0, which is to say this section right here, when x is greater than 0, we know our derivative is actually positive because we're increasing. So we're greater than 0. We have a positive slope, meaning we are greater than 0. Let's kind of detail that on our graph. So all we have is this information right here. We have our increasing, decreasing. We got our critical point. There's no point of inflection along this parabola. So we can kind of just sketch accordingly. So we can kind of just draw a line, that, boom. Maybe not perfectly straight, but let's kind of take a look. So in this area where x is negative, the area I just circled, it says, because this is a graph of y prime, that our derivative is negative. And if we check where x is less than 0 on our normal graph, our derivative is less than 0. Perfect. Now let's check on our derivative graph when x is greater than 0. Okay, looks like our derivative is positive because this is the graph of the derivative. We check over here on a normal graph. Our derivative is definitely positive. You can draw a bunch of tangent lines that have a positive slope along this graph. Perfect. All right, before we continue along, it's an important distinction to recognize that what we're tracing is not just the graph. You might be tempted to just kind of follow the graph, but then you'll realize you're not actually sketching the derivative. The derivative, or a derivative graph per se, is a plot of the derivative value or the slope at every single point along our graph. And that's where that estimating thing kind of came in handy, the suggestion I had. So let's say we look at x equals 1 on our original graph. If you kind of estimate that slope, rise over run, it's kind of, let's do it. Let's do like a slope, whatever. If you did a slope between these 2 points, you would act, if this was a parabola that was x squared, you would get a slope value of. So another mistake I made here, I did say the slope here is 1. Technically, the line that I drew, it kind of looks like it has a slope of 1, but truthfully, if this is y equals x squared, the slope at this point is 2. I didn't draw it as accurately, but we're still within the ballpark of estimating our slope. So the point still kind of stands. Just keep in mind the number is a little wrong, and I apologize. 1. If we look on our derivative graph, our value approximately, even though I'm not too accurate here, I mean, could be more accurate, but it's approximately 1, meaning our slope at that point is approximately 1, and that's exactly what our derivative graph, y prime, shows us. So that's just important to recognize as we continue going into more problems, but don't worry, we'll get more practice. All right, now our second problem, it looks like a cubic function of sorts. So now we're also going to sketch the derivative of this graph. So let's kind of do the exact same method. Let's look for our critical points or point of inflections, and let's go from there. So this graph doesn't look like it has mins or maxes, but it does look like it has a point of inflection because we're changing concavity at x equals 0 on this graph. If you notice, over here we're concave down, but over here, oh, oops, over here we're concave up. So we know that we're going to have a local or just a local extrema of sorts at x equals 0, meaning we're going to have something like this or like that along our graph. Local extrema on our derivative graph, that is. So we can kind of plot that down. Okay, now let's look at how we're increasing or decreasing at certain points. So it looks like along the entire graph, we're increasing. Doesn't matter if our rate of increasing is decreasing or whether it's changing or not, but over the entire graph, we're actually increasing. So we can kind of show that on our derivative graph. So since we know that it's increasing the entire time, we can kind of just eliminate the any negative derivative values, meaning we're not going to have a y prime value that's less than 0. So we can kind of just cross everything out right here. I'll erase that crossed out, but we just know we're not working there. So now we can even approximate slopes at certain points. So let's take this. Let's say this is y equals 1. This that I just circled. If we approximated the slope right there at that point, it's not perfect. Let's do like some simple rise over run. 1, and then 1, 2. Let's say that just has a slope of 2, or actually if that was like 1. So that has a slope of 1 at that point. Don't get too stuck on my estimate values and the numbers, just focus on the concepts approximately. So we know we're going to be positive there. And then let's just look at this point. Let's do a tangent line right there. We still have a positive tangent line, and it also looks like it has a slope of 1. So we know at both, let's say this was -1, and let's say this is +1. We know at both of those points we have a positive derivative value. We have a positive slope, and they're both equal to 1. So we can kind of detail that on our derivative graph, y prime. I know this might look a little confusing because of my coordinate plane that's kind of arbitrary. It doesn't have like consistent values. Like for example, I would have -1 over here, 1 on my derivative graph, but these have like 2 spaces. The scale is different, but the idea is the same. And then I guess we could approximate more values, but we can kind of just sketch from here. Boom. So it looks like we just have a parabola, and then we can just kind of continue it from there. Boom. So it looks like we just sketched the derivative there. And this also shows us something very important. The derivative value at this point, which I'll actually do that in orange, on our original graph, on our point of inflection, it actually is equal to 0, or y prime equals 0 at that point. However, that doesn't actually mean it's a local extrema. It doesn't mean we have a min or max, which is important to recognize. So whenever you see something where the derivative value is 0, it doesn't actually mean that we have a local extrema. It doesn't actually mean we're going to cross the x-axis at this point and change our rate of change from like positive to negative or negative to positive, whatever it'll be. So don't fall for that trap in case you see that like on a test or something. Another thing we should notice is on our derivative graph over here, or I'd rather circle this, we have this value which is an extrema or a local min in this case on our derivative graph. So we have a local min. And if we look on our original graph, that was a point of inflection. So now we know, and we can actually write this out in words, point of inflection on y, so let's say y is just the original graph, equals extrema, or local min or max, on y prime. So there's a kind of a pattern to understand. And in case any of this was kind of confusing, we can see that our slope across this entire y value is positive. We're positive everywhere. So therefore, on our derivative graph, y prime, we notice that we're positive. Our slope value is positive for practically every value except at x equals 0, which is 0. But we're still not negative. We're negative nowhere on this graph. Additionally, I believe it's important to understand concavity when drawing our derivative. Essentially, what concavity is, it's just the sine value. So I can write that down in case you are not aware. Concavity equals the sine value, so positive or negative, of our second derivative, which in this case is y double prime. So it's essentially the rate of change of our slopes. Like that might be a little confusing, but let's take a look. So let's just look at this graph. So let's look at our original graph of just y, this kind of cubic function of sorts. So let's just break this section into its own thing. And how did I know where to break this up? Well, I did it through the point of inflection, because at the point of inflection, that is where our second derivative is changing signs. And that's where, and as we know, our second derivative has to do with our concavity directly, whether it's positive or negative, and that's how we separate them, kind of independent of sorts. So our concavity is essentially how our rate of change is changing. So let's take the derivative down here. Our slope is pretty steep. So our slope, and then we're going to change that right now. So our slope's pretty steep right there. But then if we go to this point right here, our slope is less steep. To say it's less positive, meaning our slope is actually decreasing. Because then if we draw another line, actually I'll keep those there. So we have a line right here, we have a line right here. Slope seems to be decreasing. So slope decreasing, which means our our concavity equals down. We're concave down because our slope is decreasing. Slope is decreasing there. We're becoming more negative of sorts. Or we're getting closer to like a negative value. So our slope is actually decreasing there. Now let's isolate this top area to explain concavity a little more. Continue elaborating on it. All right, we'll draw it in pink. So once we got to this value of x equals 0, we know our first derivative is 0. Our slope is 0. So let's just draw a tangent line right here. Our slope is that, but then if we draw a point up here, our slope is even greater, which is to say our rate of change of the slope, meaning our first derivative is increasing, which means we are concave up. And our slope, it is concave up because our slope is increasing. We are becoming more and more positive, more and more positive. And we'll continue exploring this idea on other graphs, but let's look at our derivative graph. So let's look at the left side. So we know our slope is decreasing. If this is a graph of our slope, yeah, it is decreasing. It's literally decreasing. Our y prime value is getting less, smaller, and smaller. Now let's look at the right side. Our slope is increasing. We're concave up. Yeah, our slope is increasing. It's becoming from a value of y prime equals 1, y prime equals 4, like as we go more and more, and our slope is increasing. So that's essentially a little thing about concavity and how it reflects on both y prime and just y itself. And remember, concavity is just the sine or value of y double prime, which is essentially just means it's the derivative of our derivative graph. And then I'll explore this idea a little bit deeper. So let's just say we actually made this graph smaller, just for now. Make it a little smaller. Let's duplicate it, just so I can show you a graph of y double prime. I won't do this for the others, but I will do it for this one because on polynomials, it's most apparent. Again, same mistake with y double prime. It should also be in the apostrophe, which I will show on screen. All right. So essentially, y prime, we can just act as the left graph is our original function, and our right graph is our new derivative. We can essentially just sketch it just like we did with the parabola originally on the problem earlier. So we actually know that's just going to result in a line because we just did it. But let's say we didn't. So let's look. We're actually decreasing, we are decreasing over here, increasing over here, and then we have a change of direction at x equals 0. And that's exactly what we just mapped out here, which, if you remember, that's exactly what we did in this problem essentially. But if you look, as I said, concavity is just the sine value, positive or negative, of y double prime. Let's look at y double prime. Let's just kind of write it out. At x is greater than 0, which is essentially everything right here. X is greater than 0, y double prime, because it's a graph of y double prime, is greater than 0. It's positive, meaning we are concave up right now. But if we look in this section, x less than 0, when x is less than 0, y double prime is also less than 0, meaning we're concave down right here. And that's the same thing you could see over here. Their slope is decreasing, or we have a decreasing graph over here. And then how does that look on the original function, the concavity? Because remember, this is negative concavity, meaning we're concave down, concave down. Over here, we're concave up. How does that look on the original graph? Here it is. There's a lot of stuff over here, a lot of lines, kind of busy, but we can see that it's kind of that curvature that shows you concave up or concave down. Here we have a decreasing slope, but on this right side, we have an increasing slope. That's to say positive, which is exactly what we showed right here. That might be a little confusing, and I apologize, but I just wanted to touch on second derivatives and how that'll kind of help you graph these functions. All right, that last example was a bit lengthy, but I just want to explain a lot of important things, even if it's just an introduction on those things, such as concavity. But let's look at the next problem. So this looks like a sine graph of sorts, because we are oscillating, which oscillating is just we were going like this, kind of oscillating around the same values, staying around the same values. So let's sketch the derivative. So first, let's look for a local extrema. So it looks like we would have one right here if it was continuing, because it's a sine graph. But let's say we didn't know it was a sine graph. So let's look at our actual local extrema. So we have one right here, and we have one right here. And actually mark down these points just to make it a little easier. This local extrema that I just circled is at x equals -2. This other, or negative pi over 2. This one is at pi over 2, but that's not too important. I just wanted to show it for most accuracy, of course. So we know we're going to cross the x-axis at these points on our derivative graph. So we can actually just go mark those down right now. So there we go, at x equals, because this is our derivative graph, y prime, x equals negative pi over 2, and then pi over 2. So we know we're going to pass through the x-axis of some sort eventually. And then let's see what else we got. Looks like we have my mistake. So it looks like we have a point of inflection at x equals 0 on our on our original graph. Remember, this is original graph y. So we have a point of inflection right here, meaning we're going to have a local extrema on our derivative graph. So we know somewhere right here we're going to have a local extrema. So we'll keep an eye out for that. All right. So now we can kind of start to sketch. So let's look at our changes of direction. So right here, and if you wanted to test yourself, our slope is it's becoming more negative. Right here we're around 0. Right here we're even more negative. So we are concave down right here. And then as we switch directions, we become concave up. That actually acts as a point of inflection as well. Or this acts as a point of inflection. We become concave up at negative pi. So we know we have a local extrema at negative pi as well. At 0. We also have 1 at pi. All right. So let's do this again. So we just have a negative slope. We're still decreasing right here, negative slope. But everything from negative pi over 2 to pi over 2, we're actually increasing, positive slope. And then once again, after pi over 2, we're just decreasing again. So we know from negative pi over 2 to pi over 2, we're going to be concave up, meaning, or I'm sorry, let me take that back. Not necessarily concave up, but we are increasing. So we know on y prime, our derivative graph, we're going to be above the x-axis. So we can kind of just draw it there. Boom. All right, and then why did I go to y prime equals 1 at this point? Well, if you approximated the slope at this point, you would get 1, but it doesn't have to be perfect for most examples. I'm just doing this for most accuracy. But for most examples, as long as you showed that this area is above, actually, As long as you show that that's above, as long as you show that that part is positive, this section that is in green, you should be fine on your derivative graph. Now let's do our areas where we're actually decreasing. So it looks like from negative 3 pi over 2 to negative pi over 2, we're decreasing, so we know we're going to be negative. And then why did I go back up right here? Well, actually, that's kind of weird. Well, because like I said, we also have a point of inflection right there. So I knew it was going to be a local extrema on our derivative graph. Let's let's try it again for the most right-hand side. So I already said there's going to be some kind of local extrema on our derivative graph, some kind of point of inflection at pi. So let's go take a look. We're decreasing. That's right here. So we know we're going to have a negative value. So we're decreasing. Yeah, Andrew, this is kind of strange. But point of inflection right here, which means we're going to have that local extrema. And then we're going to cross again right here at 3 pi over 2. Or actually, you shouldn't draw it that far. This is a normal sine function, or this in this case is cosine, because the derivative of sine is cosine. Not important for today, but if you did need to know that, there you go. So essentially, we just drew the derivative of our sine graph. Perfect. And I can erase these circles I drew. How do we know all this? Let's do a check. So if we look at our derivative graph, we know from negative 3 pi over 2 to negative pi over 2. We're decreasing, meaning we're negative. We're negative right here. Great. Now, let's go back. We're increasing from negative pi over 2, which is right here, to pi over 2. Let's go check. Negative pi over 2 to pi over 2, which is right here. Yep, looks like we're positive, which is great. Good job. All right. Now let's look at our last segment, pi over 2 to 3 pi over 2. 3 pi over 2. Looks like we're decreasing. Let's go check on our derivative graph. We are negative. Perfect, meaning we have a negative slope at that point. So if you've noticed on this one, it seems like we're kind of oscillating. And that's kind of the big point on these trig functions. We will continually oscillate, especially cosine and sine. So let's say we have the derivative of sine of x. We're just going to get cosine x. And it'll just continue to oscillate back and forth between these same values. And these functions especially because they're just going to eventually become itself. Like if we took the second derivative of sine x, or essentially the derivative of cosine x, we would get negative sine x. And then if you see, it's just going to kind of repeat. And we have the derivative of negative sine x. You're going to get negative cosine x. Then if you take the derivative again of that negative cosine x, you'll get sine x, and it'll continue to occur. So this one is actually infinitely differentiable. Not that that's too important, but I think that's just important to know. So now we've kind of seen oscillation, and we've seen how a function can continually flip from a decreasing slope to an increasing slope, back to decreasing, back to increasing, and it'll just happen along these graphs, essentially as x approaches infinity and x approaches negative infinity. It'll oscillate between these two values of whatever the function is. And let's just take a look at concavity for a second, although it does constantly change in this one. But let's just kind of take a look at our mins and maxes on our derivative graph. So we know we're concave down because we're facing down at x equals 0. Or yes, we're facing down our derivative graph. And if we look at x equals 0, it looks like we have a point of inflection, meaning we're going from a slope that is increasing. Let's check if that's right. Yeah, we have a slope that's increasing. We're getting more positive. And then we start to decrease. Look, our slope is slowing down. And then we start to decrease. We start to approach a negative slope. Our slope becomes less positive. So that's an example of one of your mins and maxes on your y prime, your derivative graph, and how it shows on your regular original function. And you can see the same on this point. Actually, I'll just circle all of the points of inflection on this graph, and I'll show how it mirrors on the derivative graph. So there's just another example of how to see your points of inflection, which show up as extrema on your derivative graph. That's an important thing to remember, and I'll keep hammering it. All right, so here's another example. Let's identify everything that we have first in our original function, and then we'll sketch the derivative, but after we've identified everything, it'll be a whole lot easier. So first, I'd like us to take a look. What looks different about this graph? Well, if you can see it, we have an asymptote, which I will draw in pink. We have an asymptote along x equals 0 asymptote. Meaning we're going to have slightly different behavior, meaning our slope actually doesn't exist at x equals 0. In fact, the graph doesn't even exist at x equals 0. Let's also take a look if we have any points of inflection, if we have any points of extrema, or anywhere where our derivative is 0, our slope is 0 rather, but looks like we don't really see a slope of 0 anywhere along this graph. I mean, we're going to get kind of close to a slope of 0 eventually as the rate of change becomes negligible. But we don't actually have any points where the derivative is 0. So we know there's no points of inflection and there's no extrema. So what we're going to have to do is we're just going to have to basically estimate our rate of change and go from there. But first we can identify what's actually happening across this entire graph, which I will draw in red. So as we see, if we start from left to right, so let's think on the interval from negative infinity to 0, basically this entire section right here, our graph seems to be decreasing, which means we have a negative rate of change. So if we draw a bunch of slope lines, if we do it in line, that looks like it's a negative slope. That looks like it has a negative slope. That looks like it has a negative slope. And we just continually have negative slopes. So I'll just erase that. All right, so we know we're decreasing. So we can say y prime, basically our rate of change, our derivative, is less than 0. All right, so now that we've established that our derivative value is 0, we are decreasing. Now let's take a look at our concavity. So let's prove this just based off looks and what's actually happening here. So if we draw a slope right here, or let's draw one at this value x equals 1. That looks like a slope about -1. And this is a smooth curve that doesn't change direction, so let's draw like a line down here. The slope looks a lot greater. I mean, that looks closer to like, I don't know, m equals -9. M being slope, by the way. M equals slope. Just remember from like m equals y2 minus y1. So anyways, that's just what I'm using in this example. But if we see, our slope is just decreasing. Our slope is becoming more and more negative. What does this mean? This means that we're concave down. And if you remember, basically concave down, concave up is essentially just the sign of our second derivative. So we know y double prime is also less than 0 because it's a negative value. So we've established that on the interval negative infinity to 0. Now let's take a look at this section right here. So it looks like we're also decreasing. And what does that say? Well, if we think about our first derivative, it's essentially just our rate of change. We are decreasing overall. So we can say our derivative, y prime, is also less than 0. All the tangents you draw, one that's to x equals 1, another one that's, let's say, x equals 5 or something, they all have a negative slope, meaning our derivative value, y prime, is less than 0. Now let's think about our concavity. Remember, concavity deals with how negative or how positive your slope is increasing. So let's put that into action to make it a little more simple to understand. So let me erase these. Or actually, I'll keep those lines. Let's say I drew a slope, or let's say I did a line tangent to the point x equals 1. I know it's not to scale right here, but same like the other problem. That's just how I did it. It doesn't mean like each individual line is 1. All right. Let's say the slope there is 1. Now let's draw a slope over here. Looks like our slope, instead of being more negative, like over here, our slope is actually started to become more positive. That looks more like a slope of 1/3 or so. And if we go left before it, looks like the slope's actually greater than 1. Or it's like, oh my bad, I'm so sorry. This should be a negative. In fact, this, so yeah, -1. Then this should be like a -1/3. This is not necessarily accurate, but this is just to show that this is much more steep than this. So that means our slope is becoming less negative. And in other words, more positive. We're getting closer and closer to a slope of 0, which wouldn't on this graph, but basically closer to a positive slope, which means right here we are concave up. And what does that mean in terms of derivative and stuff? That means the derivative of our derivative, or in other words, y double prime is greater than 0 here. Now that we have all this information, we could do our derivative graph. So let's start from the left. We know we have negative slopes all throughout. In fact, everywhere we have a negative slope. So we can know that a positive y prime value is just not going to be possible on this graph. So anywhere above the x-axis is not going to happen. So this entire graph is going to stay below the x-axis. So let's draw it in blue. So as I said, let's estimate the slope at certain values. And -1, our slope is about, it's about -1. So you can kind of draw that in. Oh, just to clarify, -1, 1. Okay. And then let's also do this as -1 and 1. So we said that the slope value was -1. Remember, this y-axis is all slope values, while the x is the same everywhere, right? And we also said at x equals 1, the slope was also -1. So we can draw that over here. So now we have our 2 points. We don't have any points of inflection. We don't have any critical points, but that's okay. We have everything we need. So if we take a look over here, the more leftward we go, the more towards negative infinity we become, our slope becomes less negative because it obviously gets steeper and steeper as we fall down, but it becomes more positive in a way. So we know that we're going to be less negative, meaning we'll probably be moving up this way. How else do we know? We also determined that our second derivative is less than 0. So that means that we are concave down. So we know that our curve is going to be down facing like that, but then I'll just kind of draw it in here. It's not perfect. It won't be. Boom. All right. Perfect. It should be more rounded out like this or more like that, but that's okay. It's not going to be perfect. And then we have an asymptote along here. The asymptote's going to change because since we don't have any part of the graph there, how can we differentiate it there? It's just not possible. So I'll draw an asymptote. I'll do it in line. All right, perfect. Now let's look at the right side of our graph. So we know we're still decreasing, and like I said, any possible positive y prime value, which actually, quick distinction, I'm sorry, this is not y prime, that's just y1, but it actually should be up here. I will make a disclaimer in the beginning of the video to clarify that, but it's actually not supposed to be down here. Y prime is like that. And I've actually been writing it that way over here. So I apologize if that was a bit confusing, but as you're watching this video, there should be a disclaimer at the beginning. All right. So going back to what we were saying, on the interval, let's say this interval is 0 to infinity, we're negative the entire way. So we know we're going to be down here. But our slope starts pretty negative and it becomes more positive. Or to say that our second derivative is greater than 0, meaning we are concave up. So we'll kind of draw it accordingly. So let's say if we drew this line as a bunch of slopes, we have a pretty negative slope because we're way down here. But we become more and more positive, or we become less and less negative. So our y value as we get to the end over here is, let's say, it'll be more positive, or it'll be less negative rather, because it's not actually going to be positive. And then we can kind of just sketch the graph. That'll continue going along with an asymptote. All right. It's also important to note that on the original graph of y, that function which is 1 over x, we're also going to have an asymptote along y equals 0, or essentially the x-axis. We're never going to touch that point, and because we're never crossing and our function just kind of skates along the x-axis, we're never going to have a slope of 0, and that's going to be reflected on our derivative graph because we will never intersect the x-axis, meaning we'll have that same asymptote. And then just to kind of reconfirm, we don't have any critical points. We don't have any points of inflection, but we were able to do this one by understanding concavity, understanding obviously y double prime as I just said, and y prime, and just kind of estimating the slope at certain points. All right, now let's go look at a linear function. Now, no more curves, the polynomials, just a linear function. So we just have this constant slope. In fact, we can calculate the slope anywhere. If we calculate it right here, calculate between these points, rise over run, m equals 2. 2 over 1, technically. That equals 2. All right. So we can say that this line is like 2x. All right. That's not too important for any, but this is just an important point to understand. So if we remember, y, or rather the derivative of y, which if you wanted to write this a certain way, it's just like saying dy dx equals y prime. So when we take the derivative of y, that's essentially just the slope of the values. It's a graph that has all the slope values along your original function. So if we continue estimating slope values along this, or not estimating, but rather actually getting it, right? Run 1, rise 2, we still keep getting the same slope. We have a constant slope. So if we're saying that the first derivative merely just details the slope of your original function, if it just maps it out on its y prime values, and again, this should be y prime, then we would just be having a straight line essentially. So let's just say this is the value 2, and we would just have a straight line. And this line on the left, this linear function, this has no concavity. And remember, concavity is tied to y double prime. Let's kind of show that out algebraically, just so it kind of makes some more sense where it comes from. So let's say we have y equals 2x. Now let's take the first derivative. Y prime equals 2. Now let's take the second derivative. Y double prime equals 0. Now first I'll talk about this one. This is why it has no concavity. If you remember, concave up, write this in green, concave up meant that there was a positive value for the second derivative. Concave down meant there was a negative value for the second derivative. However, here we have a value of a 0. That means we don't have concavity here, so we don't really have to worry about this one. But what we do have is our y prime value, or first derivative, which I should get used to seeing this as well. Same thing. That equals 2, because we just do our power rule. 2x, and then the derivative equals 2 x to the 1 minus 1, and you multiply this by 1, you move that forward essentially. Then you just have 2, because that's 2x to the 0. So as we see y prime equals 2, we see it on our graph right here. So this is just an important thing to understand. A linear function, let's say that has a constant rate of change, it's going to yield to a straight line of y prime equals just a constant, just a constant. All right. So now let's use our skills. We just learned that a linear function of a constant tied to an x, so just a standard linear function, yields to a straight line. Now we have just two of those functions intersecting, which is actually an absolute value function. Let's say this is y equals the absolute value of x. Not just to note, just to note. All right. So we have this function right here. And we know that these lines are going to yield to straight lines where y just equals a constant. But we have them from two different directions. So what do we do about that? So we're going to essentially do the same thing, but we're just going to map it out. All right, so let's just take a look at this section first. So just one at a time, as I always say, or as I've been stressing. So let's just do the slope. So we got, let's do this point to this point. Might not be perfect, but as I said, this is supposed to depict the absolute value of x. So that means it is going to be two values, one where it's y equals x and then one is y equals negative x. So we know, but we basically know that the slope here for every rise, the run is equal. So we know y equals negative x, or essentially the slope on this section, slope is -1. We've already established that. We don't have to worry about concavity or anything because, as I've said, we will just result in a second derivative value of 0. We'll run into a second derivative value of 0. And as I said, a concave up is positive, concave down is negative, but nowhere does it state for either of these that a second derivative of 0 means any of them. In fact, it's just in the middle. So we don't have concavity for this one. We don't even have to worry about it. All right, now let's do the right side. Let's do the same process. Run. Let's basically just do the slope between these two arbitrary points. Slope equals 1. So we have two different slopes along this graph, which is usually fine because if we have like a normal polynomial, we have many slopes. We have so many slopes. In fact, this entire graph that I just drew right here can be said that's made out of a bunch of individual slopes. All right. So now how are we going to graph that? Let's graph the left side first. So it's and the slope is -1. And remember, our slope, just remind you, is our y prime value. So let's put it in. I'll do it in red. All right. So slope y prime is -1. M equals -1, the slope. So we'll do it down here. So we'll actually do this, -1, 1. All right. Something like that. Or just for this section. We'll do it up to here. Perfect. All right. Now let's do over here. Our slope is 1. Our y prime value is 1 for anywhere on the interval 0 to infinity. Over here is -infinity to 0. Anyways, let's draw that out. So we have a slope value of 1. So we can draw up here 0 to infinity, 1. In fact, I'll draw an arrow. Now here's our problem. We're not meeting the same point. So what does this mean? Well, if we look back to limits, if we think about limits, the idea of a limit, we have to be approaching the same thing and it has to be continuous. It has to be a smooth sort of graph. So yes, I mean, we might be approaching the same value of 0 from the left and the right, but we're doing it in different ways. And as you see, we have different slopes, so we don't even approach the same value over here. So we can say that we have holes right here, so we can draw that as just holes. That's how we do the derivative of this graph. But as I said, back to limits and continuity, we have this we have this sharp corner where our derivative is not changing very smoothly. I mean, it's such a harsh, it goes straight from -1 to 1 if this was slope value. If for our derivative graph to be smooth and continuous, it would have to go from -1, and then it would go to -0.999, and then it would go to it would just keep gradually changing its slope value until it changed to 1. But since it's so sharp for a derivative, it's not differentiable. It's not differentiable. We know that from our limit rules, and we see that on our derivative graph. It's not differentiable at the value x equals 0. Not differentiable. But this is not to say that it's not differentiable anywhere else but there. We still have that slope. Remember in our previous problem, a constant slope yielded a straight line, and we see that here for both sections, the negative infinity to 0, which we see right here, the slope of -1, and the 0 to infinity, our slope of 1, not -1, just 1. But since at this value, not differentiable, we just write in holes right here to show its discontinuity. All right, so now let's take a look at this exponential function. So the tricky thing about exponential functions is their derivative, their slope of their respected y values, they're pretty similar. I mean, they're going to grow at the same rate at least, to say y and y prime. They're going to be pretty similar. So I would just recommend estimating 3 points and then just kind of sketching it from there. It's going to follow the same shape for the most part, though, just slightly different. All right, so let's take a look at x equals 0. If we were to estimate the slope, let's say this is 1, 2, 3, 4, just a normal scale. 1, 2, 3, 4. For to estimate this, we're on 1, rise 1. That means our slope, if we're between these 2 points, at this point, the line tangent to x equals 0. The slope is about 1. Or to say, at that point, f prime, or I'm sorry, y prime equals 1. So we can actually go draw that, or go draw that in over here. It says 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, let's go with it. In fact, let's do it in pink. All right, now let's go look on the left side. So if we drew a line tangent, it's the positive slope. In fact, everywhere across here is a positive slope because we're always increasing. So for that reason, we know we're not going to really be touching the negatives for this graph. We know we're just not going to. We can rule that out. But if we take a look at the slope over here, the slope doesn't look too great. In fact, it looks like a small y prime value. We don't even need to estimate it. We just know it'll be somewhere over here, very small. Now let's take a look at our y value up here, like our y prime. So we can kind of estimate if we did a slope, let's say tangent to this point or so. So if we got a point right there, and well, it's kind of tricky to estimate, but let's say that's about 1. The slope is pretty great. I mean, 1, 2, 3, 4, and honestly, my thing's a little off scale. But the point is, the slope is pretty close to what the y value is, so it'll be probably somewhere up here. That, just to say this dot's not necessarily accurate, but we can just kind of sketch off that. Whoops. In fact, that's a little sharp. Boom. So as you see, it carries the same shape. How can we prove that shape further? Well, this is concave up because our slope is increasing. Over here we have a pretty small slope, but over here, I mean, our slope is pretty great. So we know that our y double prime is greater than 0, same as our y prime. It's luckily enough, or funny enough, same as our y value, but that's not important. Anyways, we know we're concave up. And let's take a look at this in an actual exponential function. Let's do some math to prove it. Let's say this is y equals e to the x. The funny thing about this one is the derivative, the derivative of e to the x is actually just e to the x. So this is infinitely differentiable and it'll continue giving you e to the x. So remember, we can prove that y double prime is greater than 0 because if you had any value, if you had, let's say, any constant raised to the x power raised to the x, let's say you had even like a negative 1000, 0, 1, 0, 0, 0, 0, 0, a bunch of zeros, you'll still get a positive value. Keep in mind, it'll be a really, 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 really small decimal, but it'll be a really small decimal, but it won't be negative. So that's how we can prove it's concave up, and that kind of further proves that our sketching of the derivative here in this case was correct.
All right, and so for our final question, let's take a look at a piecewise function of sorts. So we're still going to sketch the derivative, but now that rule where I was saying we should break it down part by part on the graph, that's really going to be most important because a piecewise function is essentially just a function made up of many separate functions. So let's take a look. So if we wanted to break up this graph, we could technically, from what I see here, we can break it up. This is one that looks like a cubic function of sort, which you could actually write down because that's going to be kind of helpful. I'm doing dot to dot, or for the most part. And then right here, looks like we have some sort of linear function. And then after that dot, and all the way to here, we have some sort of quadratic function. Then right here, we just have a line, so it's also linear. Right here, we have a semicircle. And then right here, looks like we also have a linear function. All right. So now that we've broken them up, we can go section by section and just do a derivative right there. And then we can just continue with the next section and the next section and the next section. But yeah, so let's take a look at the first section right here. So it looks like we're some sort of cubic function. I guess we could start at the top or near the top. Looks like we have a pretty negative slope. In fact, throughout the entire part of this graph, we do have a negative slope. So we know for this section, which is -6 to -4, which we could actually just kind of highlight over here, we're not going to be positive at all. Like our slope is not going to be positive. It's completely negative. So we know we're going to work down here. All right, so -6, -4. So it looks like that's a pretty great slope. But then our slope seems to increase. It seems like we have a point of inflection. It becomes more positive right here. In fact, the slope at this point is 0. So it looks like we have some sort of point of inflection. And then we continue increasing our slope after that. So that's why that's a point of inflection. We actually change our concavity. Up here, we are concave up. And then over here, we are concave down. All right. So now we can kind of draw that. So let's go to our derivative graph. So let's go over to our derivative graph and let's draw that in. So we know that we have a slope of 0 at -5. So we're actually just going to bubble that in because it'll be easier. Now, we know that our slope, since on this section, we are concave up, our slope is actually increasing at this first section from -6 to -5. So we know that over here, we're going to be increasing before we get to -5. And then after -5, our slope goes from 0, and then it becomes more negative and even more negative. So we know we're going to be decreasing. Our slope's going to be decreasing after that point. Remember the second derivative. All right, and then we can just kind of sketch it. Doesn't have to be perfect because we don't have exact slopes here. So we'll just do something like that. Great. Now another thing you can kind of notice, and a kind of good rule to follow, this is a cubic function, right? And over here, it seems like we got some parabola of sorts. And if you go back to our other example, we had a cubic function, and that yielded us a parabola for its derivative. So that's something good to know. It's always going to be, for polynomials, it's always going to be a degree lesser. Obviously, you can't guarantee each of these is a polynomial function, but it's just a good rule, especially when you do know that you're dealing with a polynomial. All right, now let's do our next section from -4 to -2, which we noted was linear. So, since it's linear, we're sketching the derivative, which is just the slope. We literally just need to find the slope at this point. So we can kind of do it by rise over run, or the slope formula, whatever you like. We're going 1, 2 for the run, and then it looks like 1, 2, 3. So it looks like our slope right here is 3/2, and it's positive 3/2. So we know we'll be working up here, 3/2. So we'll draw it from -4 to -2. Wait, that's not perfect, I know. But yeah, -4 to -2, around 3/2 or so. So 3/2 would be around here. So -4 to -2, around there. Perfect. Now you might notice, why are these not connected? These, like on the derivative graph, these two lines are not connected. Well, remember, this is a piecewise function, and let me kind of explain this. Since our slope changes instantaneously right here, like let's say if we're looking at our cubic function of sorts, let's say we have a slope of -6. We jump straight instantly to, oh, I didn't mean to erase that for. We jump instantly to a slope of 3/2. Meaning we don't gradually go from -6 to -5.99, and then to eventually -5.89, and whatever. So it's not a smooth curve. So therefore, that area is not differentiable. So at that point on our derivative graph, we can just write that in as a whole. So as a whole. Boom. And then we can kind of test that. So we know, or just a big rule to know, that the slope, basically, if we look at the slope formula, or not the slope formula rather, but the definition of the derivative, the slope of the left side has to agree with the slope of the right side for it to be like continuous and differentiable. And if it doesn't, then we cannot do that, or we can't connect them. So let me just keep going and we'll show more examples. So right here, I know you can't perfectly tell, but it kind of does look like we go from this linear line, if we're looking at this next section. We go from this linear function with a slope of 3/2, and we go straight into a parabola of sorts. And it looks like it's a smooth curve right here, which for this example, I will just say this is a smooth curve. So at this point, the slope on the left and the slope on the right, as they approach each other, if we think about limits, the slope on the left and the right agree with each other, meaning we are differentiable at this point. So therefore, on our derivative graph, we won't have to draw a hole, because that area, or that point at x equals -2, which I know that looks a little weird, it should be like right there, at x equals -2, that is differentiable. So we don't have to draw a hole. So let's kind of draw that in our graph. So we start with a slope of -3/2. So we know instantly this is not going to be an open circle. That's going to be a closed circle, meaning we're going to go off from that point. It kind of blends seamlessly, if you were to say that. So we know we're a parabola, or even if we didn't know we're a parabola, we can kind of just track the slope. So right here we're positive. We keep staying positive, but then we reach a maximum. We reach an area where our derivative is 0. And that's about, let's say, x equals negative, or actually write that in, x equals -1.5, which I know that's not perfect, but we do reach a peak or an extrema. And then after that, our slope starts to decrease. Our slope starts to decrease, and it decreases at an increasing rate. We just keep getting more and more negative. So we can kind of show that. So we know at x equals -1.5, we're going to cross the x-axis. So x equals -1.5, we're going to cross the x-axis right there. And our concavity here is concave down overall, because our slope is becoming less positive. Like over here, we're at 3/2, but then we're less than 3/2, and then right here we're actually 0, and then we just become more and more negative. So we know that our overall slope over here is just going to be decreasing. We can kind of draw that in, boom. And then we just keep decreasing till the point x equals 1, which is right here, x equals 1. So we can kind of just keep sketching a graph or a curve. X equals 1. Like I said, the y value doesn't have to be perfect because we're not here to like estimate each value or each point on the graph, but we are just sketching the curve, sort of estimating it, the derivative value. All right. So now we can look at our next section, which is just a linear function. Wait, and then also pause. Remember from this rule over here where I said if we know this is a cubic function, our derivative is just going to be a parabola because it's always 1 degree less for polynomials. We also don't know it here, but based off that rule, we can know that this is probably going to be a linear function on our derivative, and it looks like we are a linear function. If we go back to our first example, I believe. All right, now we can take a look at the section from 1 to 3. Now it looks like we are also a linear function as I specified, but what is our derivative? Well, I mean, if we did a rate of change from these 2 points, let's say we had, this was y, this is the point 2, this is the first point, so then we'll just do y2 minus y1 over x2 minus x1. And even without this, you can kind of see that we are not changing at all, but here, let's just prove it out. So our y value is -3. Oops. So it'll be -3 minus -3 over, and then the x value over here is 3 minus over here is x value is 1. Then it gives you -3 plus 3 over 2. That's essentially just saying 0 over 2 or 0. So our slope is 0 right here. So just taking the derivative of that, our slope is also 0 there. Or yeah, our slope all throughout is 0. We aren't really changing. So our derivative graph is essentially just going to show that we are along the x-axis because that's the line y equals 0 for the points between x equals 1 and x equals 3. And here's another thing. Our slope changed instantaneously right here. We're incredibly negative right here, and then we instantly become like a slope of 0. So if you remember to right here, where we changed instantaneously, if the slope on the left does not equal the slope on the right, we're not differentiable right there. So we're also going to have a discontinuity on our derivative graph. So we can show that with an open circle, a hole that many people call, on the point x equals 3 right there. I'll draw it on our graph at x equals 3. Wait, sorry. So as I said, not x equals 3, x equals 1. Also x equals 3, but we'll get into that right now. But x equals 1 because the slope does not equal on the left and the right. So we can kind of draw a hole for both of them. And as I said, from 1 to 3, we have a slope of 0, so we can just draw a straight line. Boom. And then those holes just specify we're not differentiable at those points. And why do we have a hole right here? Well, I'll show you. So I was kind of looking ahead, but you might have seen it already. The slope also does not agree right here. Right here we have a slope of 0, but then right here we instantly have a very negative slope that it clearly is not a smooth curve. Or rather, it is not a smooth curve because we're going straight from this to something like this. If we were to break that down into slope, it's essentially, if we look really close, if we zoomed really close in, we would essentially see something like this. And then obviously it kind of rounds out the longer you go. But at that point, the left and the right hand slopes don't agree, therefore we're also going to have a hole right there. So that's why I drew a hole. Now we're looking at this, as we were just saying, the semicircle function of sorts. So right here, from anywhere until x equals 4, it looks like we have a negative slope, but our slope is increasing, meaning we are concave up. So our slope is becoming more positive, but we're still negative. And then after x equals 4, or which is has a derivative of 0 at this point, slope of 0, not perfect, there you go. We just keep increasing our slope. I know it just seems like I'm tracing it, so I'll kind of break it up a little more. We're becoming more and more positive of a slope. So therefore, where we know after x equals 4, our slope value, our derivative value, is going to be positive. But before x equals 4, our derivative value, or slope, is going to be negative. So let's kind of draw in that we're going to have an intersection at x equals 4. Let's kind of write that in. All right, and let's kind of estimate the slope over here. So it looks like, I don't know, whatever that is, a slope of -3 right here. And then let's say that's like -1/2, and then we approach 0. So we can kind of just draw that. All right. And after that, we just become more and more positive. And this can be more like a line. All right. And then we become more and more positive until x equals 5.
As I earlier specified, this is not completely correct, the derivative of the semicircle, so you feel free to skip ahead a little bit. I will be making revisions, and so we can take a look at what the actual behavior of the derivative of a semicircle would look like.
Now we're also going to have an open hole there because if you looked ahead again, we also have slopes that disagree. I mean, it literally forms like a peak right there, meaning our slope on the left does not agree with the slope on the right. They aren't the same, therefore not differentiable at that point either. And now we can do the last one. So we just have this linear function as we specified, and I guess we could just calculate the slope because that's what our derivative is. So we know our run is just 1, or -1 rather, and our rise is also 1. Slope formula, m equals -1 right there. So then we can just draw a line at y equals -1. And we'll draw a hole as well. Boom. All right, so now I'm here for some correction and clarification around the semicircle. So essentially where we drew the derivative as a line, and we'll kind of show that over here. I'll draw it in green, or this area rather. So conceptually, this is not wrong. Drawing the slope going from negative to positive, and finding that you had a minima of sorts, an extrema, an area where your derivative changes from negative to positive, or positive to negative, but in this case negative to positive, it is correct conceptually. However, an idea about a semicircle that is really important to understand is, here I'll draw it out. Actually, let's just draw a full circle. What if we drew a full circle, right? That's not a great circle. What if we had a circle, right? This is not a function, this is a relation, but that's not too important. So let me say if we just, let's say we just cut all this off. I just kind of want to make this functional, but I do want to show or kind of elaborate on something. So let's say we do have a semicircle. Me erasing it was not important. If we check the slope along each point, eventually when we try to go to the top, which actually, let me turn this back on. When we go back to the top and we get to like the middle part, we end up getting a slope that's undefined. Our y prime is undefined at these points, undefined. Which means if we were graphing this on a derivative graph, we were graphing the derivative of this, and then let's say this is a semicircle, and semicircle function of sorts. We are going to have these points where it's undefined, meaning we're going to go off to infinity. We're going to need an asymptote to accurately represent this.
And let's take a look. So let's look at the right side. If we go from our lowest point, we have a slope of 0. And as we get closer and closer and closer to that point that's undefined, where we have the steepest slope possible, our slope is just going to get greater and greater and greater, meaning we're going to have a slope of 200, 1,000, and we're just going to keep getting closer and closer to a point where we technically have an infinite slope, even though that's not necessarily the correct term, but that's essentially what's happening.
So here's a better way to represent this area of the graph, this portion. All right. So we know it's undefined. So we know that, therefore, we're going to go off to infinity because we don't have a point that's like we don't actually have a number value to represent it. Because this is like if we did the slope of this would eventually be like that'd be like 1/0. We don't really have a number value to accurately detail it. So let's just erase these. The holes are correct in the sort. The fact that we do have a discontinuity there. But I say we use asymptotes to more accurately model this. So we can draw it at the ends of each of our holes on our functions right next to it, or part of the function. We can draw asymptotes because an undefined, we're just going to go off to infinity on our graph in order to just best describe what the slope behavior is like as we get closer and closer and closer to that undefined point. Let's also draw an asymptote right here. All right. So asymptotes that go to infinity. So we know we're getting closer and closer and closer because that y prime value is undefined at those 2 points if we look back on our graph. Undefined if we technically got closer and closer, because if we knew this is a semicircle, maybe it doesn't look as accurate for my drawing, but I am telling you this is a semicircle. So in an example, when you do see something that's a little more accurate looking like a semicircle, then you'll know. So we know we'll just have a smooth curve of sorts that kind of skates along, and then we'll go along that other asymptote. Because like I said, we're getting closer and closer to being an undefined slope, or having an undefined slope. So that's just a better way of modeling that area of the graph where we do have a semicircle. And that's just the best way to show its derivative. And see, this doesn't necessarily mean that an undefined slope, because we can have many kinds of different undefined slopes, as we've had here. We've had many points where our derivative on our left, our slope on our left, does not equal the slope on our right. We've had many times where that's the case. But it doesn't mean that it always goes to infinity, as in the case of the semicircle. Why? Well, because the semicircle is smooth and continuous, and it goes basically up and down quickly. It goes up and down, and it goes straight from that point where it technically has a vertical tangent of sorts. So that's just why in this case this one gets asymptotes. But that's important to understand. Not every undefined slope, so like these cusps, this corner, that doesn't mean you have an asymptote. That just gives you a hole. But if you do have that point where you are going to have vertical tangents, or rather when it's smooth and continuous and just becomes straight up and down, meaning we have a vertical tangent, that is when we're going to have those asymptotes, those that go to infinity for the slope. Because if we kind of look at it, detail it really close on the semicircle, our slope is getting, let's do the slope on the right. We're getting more and more and more positive. We're eventually going to reach a point where slope is completely vertical, undefined. So that's why we have those asymptotes there.